Welcome back. In the last video, we trained our very first own custom vision transformer on the Food Vision mini data. However, we didn't quite get the results we would have hoped for. I mean, these are some of the poorest results we've got across the entire Food Vision mini project. And I issued the challenge to try and discover what our training setup is missing. And the question was, how is our training setup different to the VIT paper? So we've replicated the model architecture correctly, but what was different between our training procedure to get such poor results and the VIT paper training procedure to get such great results? So you might have a few guesses here, but here's what I discovered. So if we go into here, the first one is in the setup. So data sets. As we've discussed, our Food Vision mini dataset is quite small. There's only about 200 or so images. So data sets, to explore model scalability, we use the ILSVRC 2012 ImageNet dataset. So that's ImageNet with 1,000 classes and 1.3 million images. Then they also used the superset ImageNet 21K with 21,000 classes and 14 million images. And finally, JFT, which is, I think it's a Google private data set. I mean, ImageNet 21K and ImageNet 1K are publicly available, with 18K classes and 303 million high-resolution images. This is literally 1 million times bigger, or over 1 million times bigger than our dataset of pizza, steak, and sushi. So what does that sort of say? It's that the original VIT paper simply had more data. We had the same model scale, but the datasets that they use just gave the model more opportunities to learn. And then there's a few more differences if we come into the book version of the course that I've written down here. PyTorch paper replicating. And if we go right down here, where we're up to, we are at 9.4. So here's a beautiful table discussing that the main reason we have different results or poor results is scale. So we've learned before that generally in machine learning and deep learning, more data is better, especially with deep learning models. Here we go. In deep learning, more data is generally always a good thing, and a longer training schedule. So these are the main differences between our training setup. Our architectures are the same for VIT base. So the number of training images, they use 3 different data sets, 1.3 mil, 14 mil, and 303 mil images. Our version uses 225. So several orders of magnitude less data. And then for number of epochs, we only train for 10 epochs, whereas the VIT paper trains for different variations or number of epochs. And we can find this in table 3. So we go back up to table 3. So depending on the data set that the Vision Transformer paper authors used, also depends on how many epochs they trained for. So it looks like the larger the data set, the less epochs that were trained for, whereas a data set like ImageNet 21K was 90 epochs, which is 14 million images, and a data set like ImageNet, which is 1.3 million images, was for 300 epochs. So that's one thing that we could try, is train our model for longer, and that's something that you might want to try, is to see what happens if we would train for, say, 100 epochs. In fact, I don't even know. That'd be something to give a go. Then if we go back here, they also use different training techniques. We've discussed the batch size. We're using a smaller batch size because we're working with smaller hardware, and we don't even have 4,096 images in a single batch. We only have 225 images total. So the first thing that we could try is to use more data. And because we're using, if you wanted to try this out, Torch Vision datasets. If you wanted to try this out, you could go into the datasets, and we're using Food 101 here, but we're using a very small subset. So you could try to download this entire dataset into Google Colab and then train our VIT model on that. Using the same training setup, you just have to prepare the data into a trained data loader and a test data loader and see how it goes. Just beware that it may take a while to train because this whole data set has 101,000 images in 101 different classes of food. But if we keep going to find out the differences, there's 3 more things here that we haven't quite covered. And there's learning rate warm-up, which is 10K steps. There's learning rate decay, linear/cosine, and there's gradient clipping. And we don't use any of these. Now, these 3 things are mostly to prevent overfitting, regularization. Now, what is that? So if we go back to, I believe it was custom data sets, we jump into overfitting. This is the entire field of machine learning almost. It's the walking the tightrope between overfitting and underfitting. So if we jump into loss curves, what should an ideal loss curve look like? Recall that overfitting is the training loss is lower than the test loss. But our model is also underfitting as well. It's not performing as well as it could. So one way to prevent underfitting is to add more data. But then if you add too much data and your model has too much of a learning capacity, in other words, it has too many parameters, well, you're going to end up overfitting. So these techniques, such as learning rate warm-up, you start with a small learning rate and warm up to a certain value. Learning rate decay, as you get closer to better and better results, you turn down the learning rate. And gradient clipping, you remove some of the gradients. And I've just added resources for all of these. Let's just read what it says. So gradient clipping is one difficulty that arises with optimization of deep neural networks is that large parameter gradients can lead an SGD optimizer to update the parameters strongly into a region where the loss function is much greater, effectively undoing much of the work that was needed to get to the current solution. Gradient clipping clips the size of the gradients to ensure optimization performs more reasonably near the sharp areas of the loss surface. So it's another way to prevent overfitting, a regularization term. And of course, if you wanted to learn more about these 3 things, what can you do? Well, you can search PyTorch learning rate warm-up, and then PyTorch learning rate decay, and then PyTorch gradient clipping. How do you do gradient clipping in PyTorch? Understanding gradient clipping. Torch NN utils, clip grad norm. Beautiful. There's some resources for gradient clipping. Torch optim. Decay is the learning rate. Oh, we can do that from torch.optim. Decay. Oh, learning rate scheduler. Beautiful. And then we've got linear learning rate. And then we've got cosine learning rate, which is exactly what is in here, learning rate decay, linear or cosine. So I'm going to leave those as extensions, but the first thing I would try is to implement more data. Because right now our model is more so underfitting than it is overfitting. So the kind of way I like to train neural networks is to overfit first. So train it with as much data and as much model parameters as possible, and then prevent overfitting. So through regularization. So through terms like techniques like learning rate warm-up, learning rate decay, and gradient clipping. So I'll leave those for you to research more. We've got what is our training setup missing. Let's keep going and see if we can improve our model. We'll start by plotting the loss curves, and then we'll use one of my favorite techniques that we covered way back in section 6. So I'll see you in the next video.